Our next shuffle is Shuffle 42, which is also a repeat LR shuffle. So let's go ahead and derive the permutation representation for this shuffle. So it begins as an ordinary just left-right shuffle, and then we repeat those same actions on each half of the packet. So we go left-right again for that half, and then we go left-right for the right-hand half of the packet. So that gives us 4 pairs. Now the stacking will be as follows. 4 will go on top of 3. Now remember, this is pile 1, 2, 3, 4. So 4 will go on top of 3. That packet of 4 will go on top of 2. Those 6 cards will go on top of 1. So really, this is just a way of telling us to stack from right to left. That's all it means. Just stack from right to left. If I can pick up the cards here. Sorry about that. Okay, so what is the new ordering that we get after completing Shuffle 42? It's as follows: 2, 6, 4, 8, 1, 5, 3, 7. Writing this in Cauchy's 2-line notation, we obtain the following. The top row is always 1 through 8 in our case, and then it's 2, 6, 4, 8, 1, 5, 3, 7. Converting this to cycle notation, we obtain the following. 1 goes to 2, so we have an arrow from 1 to 2. 2 goes to 6, an arrow from 2 to 6. 6 goes to 5, an arrow from 6 to 5, and then 5 returns back to 1. So it cycles around, completing a 4 cycle. 1, 2, 6, 5. What about 3? Where does 3 go? 3 goes to 4, so we have an arrow from 3 to 4. 4 goes to 8. There we go. 8 goes to 7, an arrow from 8 to 7, and then 7 returns back to 3, completing a second 4 cycle. Color coding our digits, we obtain the following. And recall that the color coding convention is as follows. Positions 1, 4, 6, 7 are color coded black. Positions 2, 3, 5, 8 are color coded red. We do that so that we can follow what happens to the Bessey sequence structure of the packet. Okay, so applying that here, we get black 1 goes to red, which goes to black 6, which goes to red 5, which wraps around to black 1. Red 3 goes to black 4. Black 4 goes to red 8, which goes to black 7, which wraps around and goes to red 3. So we can see that each value gets sent to a value of the opposite color. And when that happens, inversion has occurred. So let's go ahead and demonstrate that inversion of Bessey sequences does indeed occur. So if we begin with our quintessential Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, it should be that after the completion of Shuffle 42, we get the inversion, namely 0, 1, 1, 0, 1, 0, 0, 1. So the zeros and ones will have switched places. So let's go ahead and perform this shuffle again. So it's just a left-right at the start. And then for each half, you perform a left-right shuffle a second time. So left, right, and then the stacking, as we've pointed out, is from right to left. So we come over here and take pile 4 on top of 3. Those cards go on top of pile 2, and all of that goes on top of pile 1. And so let's see what has happened. Did we get the inversion of our starting Bessey sequence? We did indeed. We now have 0, 1, 1, 0. 1, 0, 0, 1. And let's go ahead and take a look at the Bessey shuffle diagram for Shuffle 42. So as we see here, we have 2 4 cycles. One goes to 2, which goes to 6, which goes to 5, which wraps around and goes to 1. So that means if we begin at 1, there should be an arrow from 1 to 2, which there is, an arrow from 2 to 6, an arrow from 6 to 5, and an arrow from 5 back to 1, completing that 4 cycle. We also say that the values 1, 2, 5, 6 constitute the same orbit. Now for our second 4 cycle, we see that 3 goes to 4, which goes to 8, which goes to 7, which wraps around and goes to 3. So if we begin at 3, there should be an arrow from 3 to 4, which there is, from 4 up to 8, an arrow from 8 to 7, and then an arrow from 7 returning to 3. That completes our second 4 cycle, and it also gives us a second orbit consisting of the values 3, 4, 7, and 8. Note at the bottom here that this particular shuffle is actually the inverse of shuffle 5, which we saw much earlier in this series. So let's go ahead and remind you of what shuffle that was. So here is shuffle 5. It was a judicious RC shuffle. And recall, this is where we deal out into 4 piles. So we go 1, 2, 3, 4, and then the next 4 cards get stacked on top of the ones just placed. Okay? And then the stacking is this judicious stacking of 1 goes on top of 3, 2 goes on top of 4, and then left on top of right. So the claim is that this shuffle is the inverse of shuffle 42. Now, I don't believe that will be obvious to anyone. So let me just go ahead and we'll demonstrate it using our ordered packet. And so what this will mean then is if we perform either one of these shuffles and then follow it up with the other shuffle, it should return the packet to its original order. Now, it doesn't actually matter which one we do first, so why don't we go ahead and do shuffle 5 first. Okay, so we're beginning with our ordered packet, and recall this shuffle proceeds as follows. You deal into 4 piles. You go 1, 2, 3, 4, like that. 1, 2, 3, and then 4. And then the stacking is this judicious stacking. So pile 1 goes on top of 3, pile 2 goes on top of 4, and then we'll stack the left pile on top of the right. Okay, so it's this leapfrog stacking. You're leaping over the neighbor to the right. Okay, and then we'll leap over the neighbor there. And now it's stacking left on right. Okay, and we can show you the new ordering just so you can see what it's done to the cards. We get quite a mess here. 5, 1, 7, 3, 6, 2, 8, 4. Now apparently this ordering is going to be reordered back to 1, 2, 3, 4, 5, 6, 7, 8 using shuffle 42, which has a very different feeling to it. Okay, so shuffle 42 is the one that we've just introduced. So this is where you do a left-right, and then you perform a left-right shuffle on each half. Okay, so we go left, right, left, right. Here we go. And then left, right, and then recall for shuffle 42, top row on the right, we stack from right to left. Okay, so we're just performing the same shuffle that we introduced just a moment ago. Now what should be the case is we should get back to 1, 2, 3, 4, 5, 6, 7, 8. And we do. Those are true inverses of one another. But boy, if you perform those in succession, I don't think anyone would be able to detect that those shuffles have undone the actions of each other. But the shuffle diagrams make perfectly clear that these are indeed inverses. Because if you look at the diagram for shuffle 5 and you look at the diagram for shuffle 42 over here, they're identical with one exception. The arrows are pointing in opposite directions. So here we have an arrow from 1 to 2. For shuffle 5, we have an arrow from 2 to 1. So they truly do just undo the effect of the other. And I want to point out something I've mentioned before, which is quite powerful. So what this would mean is you could perform shuffle 5 as many times as you like, let's say 4 times. And as long as you perform shuffle 42 4 times in all, it wouldn't matter what order you perform those shuffles. So you could perform shuffle 5 twice, then shuffle 42 3 times, and then shuffle 5 2 more times, and then shuffle 42 1 more time. As long as you perform those 2 shuffles in the same quantity, the order in which you perform them will make no difference, and you will return the packet to its original order. Absolutely amazing.